Good afternoon and a warm welcome to our webinar. It's now 3 o'clock Central European Time, and it's time for us to start this webinar today. This webinar has got the title Formal Safety Verification: How to Deliver a 100% Safe and Compliant Rail Control System Without Time Delay. This webinar is arranged and hosted by Prover. My name is Lars Dahlberg, and I'm acting as the moderator and going to guide you through this webinar today. Let's take a look at what we will cover during the webinar today. So we prepared quite a lot of content for you that we really hope you're going to find very useful. So why traditional verification approaches struggle with today's complex rail systems? We're going to introduce and set the scene around that topic. Then we're going to move on and talk more about what formal safety verification is and how it really works, give you the overview of that. And then move on and talk more about how to use mathematically prove to ensure full alignment coverage, and then how Prover solutions enables early issue detection, automation, and certified safety evidence. We're also going to take quite a lot of look at some real-world results from some real customer cases. In the end of the webinar, we're going to run a Q&A. During the webinar, you have the ability to type in your questions whenever you want using the chat functionality in Webinar Geek. So just check your screens and you will quite easily find the chat function. The other participants will not see your questions and the things you will post in the chat. So we'll come back and we'll answer in the end of the webinar. We expect the webinar to take a maximum of 60 minutes, and we'll run the Q&A in the end, as I said. So with that said, I think it's time for me to hand it over to today's speakers and start with a quick introduction and see if they can jump on stage. Yeah, they jump on stage. So first of all, I would like to introduce Mr. Daniel Fredholm. Welcome to the webinar, Daniel.
Hello, welcome everybody. Nice to have you here. Hope you'll enjoy.
Maybe some of the participants have seen you before because you've been a regular speaker. It's the same thing with our other speaker, Gunnar Smith. So welcome, Gunnar.
Thank you, and welcome to all of you.
So I'm going to hand this over to both of you, and you are going to share screens between each other and go through the agenda that we just looked at. So with that, I think I'll send it over to Daniel to start.
Okay, thank you, Lars. So I will start with giving you a bit of a background and overall introduction to formal verification. So let's start with why there is a demand for formal verification. Well, if you imagine a train, that's 1,000 tons of steel that moves about 200 kilometers an hour, maybe more. And if you now imagine hundreds of such beasts that they are sharing same tracks and they are guided only by signals and software. And when everything works, when those signals and software actually works and do what they're supposed to do, things are seamless. But if something goes wrong, the consequences are horrendous. Lives will be taken and infrastructure will be destroyed. So a challenge is that today's rail control system that they have over time become increasingly complex, since they're supposed, simply speaking, just suppose that they are to handle bigger rail systems with more traffic on them. And testing and reviewing, they can catch a lot, but they can't cover every possible scenario. There are simply too many, and we will dig into that further on. So that's why regulators, they set high standards, and that's why the industry is turning to formal verification. Because formal verification is a way to prove with mathematical certainty that the software will never allow unsafe situations. So let us begin with looking at the traditional verification methods, so we know where we are today. So traditionally, verification is done by reviewing and testing in combination. Some things are reviewed and some things are tested. And this has been adequate in the past, but as we already mentioned, with the current rise of complexity of these systems that you are supposed to verify, improvements are needed. So let's get right to the point then. If we look at the traditional verification methods and try to see what the problem is with them, what are their drawbacks, and if we start with reviewing, there are three main drawbacks with reviewing. The first one is that it actually requires, what reviewing is that there's a human checking that whatever you are supposed to check, typically a piece of software, that piece of software actually fulfills requirements. And obviously this will require highly skilled personnel that you can actually trust. And such personnel are hard to find, and they take a long time to train. So these two things means that there are usually not that many of these people around, which makes it a bottleneck when developing signaling ray control systems. And also that this reviewing doesn't scale very well. Again, since it is humans are supposed to do it, and it can be hard. You cannot really speed up things or make it handle bigger sets of data by adding more reviewers, because you need to check in order for the review to actually be trustable. There are surprisingly big parts of the system that the reviewer actually needs to look at. And the human mind can only grasp so much. And the last drawback that I will mention is that it's also very time consuming. Again, since it is, although highly skilled, but still a human that needs to check that things actually are as they're supposed to be. And since it's concerning safety, they have to be very thorough. So this takes time. And this is not only a problem when you do the first commissioning of a ray control system. This also becomes a problem when you're supposed to upgrade your system. That you need to do some changes to the system, and then you need to do the verification needs to be done again, and that means that you need to review. If you did a reviewing in the first place, then you need to redo the reviews again, and that will take a long time to do. So that's the problems with reviewing. Now let's continue with testing. And testing is more automated, at least when compared to reviewing. But I say that the main problem with testing is coverage, because since what we're actually verifying when we do these verifications on ray control system, we want to establish that in every possible state that the system can be in, that the system is safe, that it will not do anything unsafe, like putting two conflicting signals that proceed at the same time and similar stuff. And this has to be checked in every possible state. So in terms of coverage, this means that what you actually need in order to be sure that the system is safe, you really need 100% coverage. So let's think about how to achieve 100% coverage in terms when it comes to testing. So if we look at this little example here, so we have 3 signals, 1 switch, 4 tracks, and 4 routes. And if we then assume that we have 2 possible states, or at least for the hardware stuff, meaning the signals, the switch, and the track circuits, that means that we have 16 Boolean inputs to be handled. And in order to ensure that all the possible combinations of these states, that they are covered by the test suite, we have 2 to the power of 16 possible states or test scenarios that we need to consider. And 2 to the power of 16 is not, it's a big number for sure, but it's not enormous. It's not astronomical yet. So this might actually be doable to get 100% coverage of this small station. But suppose now that we scale it up a bit. So we have 5 switches and 20 signals and 30 track circuits. So all in all that we have 55 objects. Then we would get 2 to the power of 55 possible states to verify. And 2 to the power of 55, that's not only huge, that is astronomical in size. So meaning that ensuring 100% coverage with testing for this, when we have this amount, even for this fairly small amount of objects, it's not doable anymore. So the conclusion then is that reaching 100% coverage with testing is not possible in practice. So continuing then, so since we cannot achieve 100% coverage when we do testing, the solution is usually to try to select what is deemed to be the relevant scenarios and test them, and deciding what scenarios are the relevant ones for the safety. That's a difficult and time-consuming task in itself, and it is also difficult, actually very difficult, to establish that you haven't missed anyone. So that's the main problem with the main drawback with testing, the coverage. But it also, just as with reviewing, testing is also time consuming. And you have the same situation when you want to do updates, then you need to run the tests all over again, which slows things down. And let me end with a nice little quote of who said it, I don't remember, but I think it kind of captures the main characteristic of testing, namely that testing shows the existence of bugs, not the absence. So just because all your tests pass, that doesn't mean that you don't have any bugs. Okay, so the solution then here is formal verification. And formal verification, in short, it's a verification methodology that uses computer tools to prove, and with prove, we mean proving in the mathematical sense of the word, that systems satisfies requirements. And it relies on modeling in a formal notation with a well-defined syntax and semantics. And there are efficient large-scale tools that can handle industrial-scale projects. And it has been used in production for rail control systems for a long time, more than 20 years. And the benefits then, well, for starters, since we're dealing with something that, since we're actually proving in mathematically that the system complies with the requirements, we get 100% coverage. Iterations, meaning that if you need to redo your verification, they are done automatically, and they are usually done pretty fast. And it also enables us to reduce the amount of testing needed significantly, since we will have captured the safety aspect will be captured in the requirements that we will verify using formal verification. So that means that when it comes to the testing, we still need to do testing. Since we need the testing in order to establish the positive functionality, that things actually happens. I mean, safety is mainly about establishing that certain things do not happen, but we also need to establish that things do happen. And for that, we need testing. But we don't need to include any safety aspects in the testing if we do formal verification. So in general, the process looks something like this. That we start off, if we start with the requirements part, we start off with informal safety requirements of some form. And informal here means not that they are sort of loose. It means that they are written in natural language. But they should be written, they are to be written in the same precise, still in a precise manner. But they are not in a format that can be handled by the computer tool that we want to use in the end. The model checker, the computer tool that actually tries to prove things. So we need to transform the informal safety requirements into formal safety requirements, write them in a format or make a model of them in a format that can be handled by the model checker. And we also need to do the same with the system. Typically, the system would be a piece of software here. And that also needs to be modeled, to be translated into a format that can be handled by the model checker. And in the case of the system, modeling the system, that can be done with a translator, meaning that we can be done by another computer tool here. So this process is automatic, whereas the process of going from informal to formal requirements is manual. So given that we have these the safety requirements formalized and the system model formalized, then we can feed these two into our model checker, and the model checker will yield a result either yes, if the system actually satisfies the requirements, or it will tell you no, it doesn't. And then it will also provide you with a counterexample. So, and that leads us to Gunnar, who will continue to bring this all up more detail and up to date.
Thank you, Daniel. If you just stop sharing there. Perfect. So I will continue on on the introduction that Daniel gave here, and talk a little bit more specifically how we can realize these benefits of formal verification and how we do that at Prover. So I will talk about two slightly different approaches to the formal verification problem. So they also have slightly different goals or objectives. So the first one is about verifying that the system correctly implements its specification. We call this specification-based verification. And the second one is to verify that the system is safe in a more general aspect. And we call this a hazard-based verification, and I will soon tell you more about why. But concentrating on the first one, specification-based verification. Here, we want to derive and eventually formalize the safety requirements from the general software specifications of the system. And these requirements are then more design specific or low level, if you will, because the specifications that you start from are not just the general principles of a railway system that the trains should not collide or so. It's more on how you actually implement that. And of course, this can be a bit different on what level of specifications you're starting from. But indeed, we're trying to verify here that the specification is correctly implemented, which is, of course, a important task. And in this case, focusing on the safety aspect of the specifications. So as specifications typically are not always clear on what is the safety part and what is more general functional part, there is always some effort in analyzing the specifications and derive the safety requirements before they can be formalized. And going back to the second one, to verify the system safety based on the actual hazards of the system. So then we start on the very top level. So what is it that we don't want to happen in our systems? What can go wrong that has safety implications? And we call these the system hazards. And the benefit of this approach is that we can find errors or issues in the actual principles of your systems, not only of the implementation. But on the other hand, it will not tell you that you have implemented your system as you intended, but it will tell you whether it's safe or not with respect to these high-level hazards, which is a good thing. So this gives us more high-level or general requirements that has also a very high degree of reusability, because these are not that different from one railway to another. On the other hand, to make sense of this, we need to have a rather detailed model of the environment where your system operates. And of course, for either of these approaches, we need to have a model, actually a formal model, as showed on Daniel's previous slide here, of the system that we're verifying. And this can be based on the design that we make a model, or it can be the actual implementation level. And doing it on the implementation level has the benefits that the implementation is a piece of software typically, and that means that it can already be interpreted by computers and computer programs. So it's typically fairly straightforward to write a translation of that piece of software into a formal model for verification. So it's not really a manual task, and it's not even a very difficult task to write such a translator. And this model needs typically to be on the specific application level. So let's say you might have a generic piece of software, but that is executing for some specific systems that you're going to implement and install. So that has the configuration data of, let's say, your track layout and all the objects in your actual system. But of course, these systems can be expressed in many different ways. But somehow we need both the software and the data for the specific application to do the verification, not only to model the system, but also to know how to represent the requirement specification for these specific scenarios. But again, once the data is available, translating that into the formal model is an automated step. So then we have a solution approver that we call prover diagnostic. And it's our implementation of the hazard-based verification approach that we just discussed. So this was originally developed together with some of our clients to tackle the problem of verifying formally the safety of interlocking systems, but it has since been extended to cover many other systems, and it can also be applied both on the subsystem and system level. So you can, for example, verify either specific functions of, let's say, a CBTC system, or you can focus on the system level and build an entire model of that and do the verification. And the goal, as we've said, is to quickly find any scenarios where the system can enter a state where something bad or hazardous will happen. And then, of course, we also want to prove the absence of such scenarios or states in the system. And once we've done that, we have established that it is safe. And these scenarios are typically on a relatively high level, so not on the code or implementation level, but it's more about how the objects in the system is behaving. So, for example, how trains are moving. And this also has some impacts on the expertise needed to analyze these scenarios. So here, it is enough to have an understanding of how the system is supposed to function. You don't necessarily, to understand these scenarios, need to know how they're implemented. But of course, if you are to fix these issues in the implementation, then of course you need to understand also that level. Right, so we have packaged this as what we call a generic package that is expressed in a formal language. And of course, it's also accompanied with the various tools that are needed, like the model checker that we saw before. But apart from the tooling, these packages contains the safety properties derived from the safety hazards. It has an environment model, as mentioned, and it tells you how to integrate these safety properties, the environment, and the system model together to build a complete verification model that is fed to the model checker. And of course, or rather, unfortunately, it's not as easy to just take this generic package and just run through the verification when you have a new application. Rather a new type of application, you could say, or for a new client or new railroad or metro. So there is some adaptation that needs to be done. So for example, hazards are on a high level very similar, but there are also more specific hazards, and we also need to make them a little bit more detailed in order to define the safety properties that we can verify. So one might have to do a little bit of modification on those properties, possibly add new ones, or just select from the library of properties that we have to make sure that you have something that is applicable for your specific setup. Then there is, of course, the creation of the system model, which, as we've already discussed a bit, is typically a automated translation step, but that translation has to be defined if it's not something that has already been developed. And then finally, there needs to be adjustment of the environment model, which may also differ a little bit from different usages of this solution. But in any case, it's a rather generic starting point that you have that you can simply adapt to your specific needs. So just a little bit on safety hazards. So on the very top, this typically includes two main types of hazards. So there can be a derailment of a train, or there could be a collision of two trains. Of course, there are variants to this as well. A train can collide with other infrastructure than another train and so on. And then starting from this top level, we need to refine it a bit so that we have something that we can actually formulate as safety requirements to verify. And when we're talking, just as an example, about collision, one such refined requirement can be collision due to a signal being violated, so meaning that the signal is overrunning red or stop signal. And that can obviously cause two trains to collide, because it's typically assumed that somehow it will be ensured that trains are stopping when they should. And then, of course, there can be hazards that are a bit more specific to the operation of a given infrastructure manager. So, for example, how to protect staff working on the tracks, for instance. There might be different safety measures there that we need to verify. Anyway, the analysis of these hazards is done with rather traditional methods that are not specific to the formal verification approach. So it can include, for example, analysis of fault trees and so on. But the additional step that we have here is that we need to also, when we have defined these properties and requirements, we need to formalize them for the verification so that they can be understood by our model checker. And then, as mentioned, we also need to have a model of the environment to be able to prove anything interesting about the system, since we have these high-level safety requirements. And it also helps to give, having a good environment model helps to give scenarios that are relevant when you do the verification. And finally, it can also be mentioned that this environment basically corresponds to safety conditions that need to be included as part of the safety of your system. If they are not fulfilled, these constraints on the environment, then your system is not necessarily safe. So, of course, care has to be taken when defining the environment model. So just some general examples on switches or point machines. We typically assume that they will not move by themselves, so they will only move when commanded to. Of course, there might be failure modes that they might lose their position for various reasons and so on, and these can be modeled too. And we typically assume that trains will move along the tracks, so that will not just jump all over the place or appear out of thin air. However, that is talking about how the train is actually behaving. In your software system, there might be, again, failure scenarios that we need to consider, like, for instance, that you might lose detection of the train so that it will appear that it's jumping around in your rail yard, for example. But that's another thing that we also need to consider. And then finally, once you are doing your verification and you start the analysis of your scenarios, you might need to add or refine these constraints for the environment model a bit. For example, you might start with a relatively abstract model on how your various subsystems are communicating. And in general, it's good to be abstract, but in some cases, the safety of the system is actually relying on some specific that we need to include in our model. And of course, care has to be taken not to over-constrain the system so that we miss scenarios that are plausible in the real system. And for that, you can use what we call reachability obligations, which is actually sort of a way to use the formal approach to establish that the system does what it's supposed to do. So a bit like testing. And you can, of course, also use testing on this model to ensure that it behaves as it's supposed to. And a quick overview of this process is starting from the left side, you have the system implementation that you want to verify. And you have the configuration data. And from that, you build a model of the system. You have on the top, the safety hazards that you derive into safety properties. So this is mainly a manual process, but there are tools, and these days often AI-assisted tools that can help you in this process. And especially the formalization process can be automated to a large degree. And then also part of the generic application, you have the environment model. All this is fed into the model checker, which will basically tell you if each of these requirements as applied to this specific system that we're verifying, if they are satisfied, or if they are not, then it will present a scenario that you can go on and analyze. So that's a very quick overview of the process. So moving to the other approach, the specification-based verification, where on the other hand, the goal is more to demonstrate that you have correctly implemented something, your specification. And this is quite a traditional verification task required by many standards, such as the CENELEC 50716. The only difference here is that we're using formal methods and formal verification to not only test it with the limited coverage, but also mathematically prove it. And the main effort in setting up this process is to define the safety requirements that you want to verify. It of course varies a lot on what level of specifications you want to base this on, and sometimes there are not even clear specifications available, so you have to do some engineering to figure out exactly what the principles are and why they are safe. And that is also an important part. What is the argument for that you actually have a complete set of requirements from a safety perspective? This is very important for the formal verification, but it's actually also important regardless of your verification method. And then again, the requirements needs to be formalized, which is a more straightforward task, with, of course, with its own challenges. And if you then in the end have requirements that are not fulfilled, you will get the counterexample scenario, which are typically rather low level. So it will tell you things about the actual implementation, values of certain variables, and so on. And then you need to interpret this to understand what is happening and why, and if that is actually a safety issue. So that requires some more knowledge on the implementation of the systems. But again, this is similar to how you would go about debugging from testing. And the process overall is similar. You have a specific application with configuration data and implementation that you automatically create a formal system model that you give to the model checker. And on the other hand, you have the generic application with your requirements, which is formalized, fed to the model checker. The model checker will tell you if all requirements are verified, then all is good, or it will produce one of these counterexamples for further analysis. And to wrap this up, we've been talking quite generically about how this is done. So using formal specification expressed in formal languages, and we have some verification tools and so on. So get a little bit more specific on Prover's offer in this area. So we have, on one hand, the formal languages. These are mainly two languages called HLL and a variant of HLL that is called SHLL, statement-based language that we use to define the generic application. So that includes both safety requirements and the model of the system, with the difference that the system model is typically automatically generated from an implementation. Then we have, for the specific application, we have a language called LCF, which is an efficient way to capture configuration data in a way that can easily be interpreted by the computer programs, but it can also be reviewed, because at some stage you will need to review that the data you are verifying is actually the data that you are putting into operation and the data that you intended to put into operation. Then we have a tool which is an integrated development environment for these formal specifications that is called Prover Studio, where you, with some tool support, can develop and formalize these specifications. Then on the tooling side, we have Prover PSL, which is our go-to model checker. So it's based on the HLL language. So you can say that anything else that we want to feed to Prover PSL is translated into HLL. And we have Prover Certifier, which is a T2 SIL 4 CENELEC compliant tool that has been assessed and certified by TÜV Nord. So it's basically checking the result of the model checker to make sure that you can actually trust this result and build a safety case around it. Then, to make things a little bit more easy to use, we have some graphical user interfaces in the tools Prover iLok and Prover Station. So they can help you with the configuring your applications, keeping track of your various verification activities, and also visualize your verification results and provide debugging capabilities so that you can see what a given scenario looks like in your signaling plan, for example, and how scenarios behave when in different executions of the system and so on. So general debug support for that. And with that, we will get into some use cases where this has been applied to hopefully get it a bit more concrete. So there I will again hand over to Daniel.
Yes. So, hello again. So let's continue then with some use cases where we actually been some use cases from our clients. So let us start. The first one is a rail control system supplier in China called Casco, and it's a major one. It's the biggest supplier for metro rail control systems, including both interlockings and CPTC and zone controllers and these kind of things. And it's also among the top 4 suppliers of rail control system for mainline rail in China. And as you probably know, or at least can imagine, that the market in China when it comes to rail is huge. I've been told that the whole of Europe is 40% of the Chinese mainline rail market. And when it comes to metro, every major city, and with major city I mean a city in about the size of Paris, has an extensive metro system, and there's many such cities in China. So Casco is a huge company, and it started off as a joint venture with Alstom, and it still is, but the majority owner is another Chinese company called CRSC, which is state-owned. And they are using specification-based formal verification, and they have been doing that for mainline interlocking since 2019. And they are currently doing the groundwork works for applying it for their metro interlockings, and that will start somewhere around next year. And they are also considering to use it for their CBTC and RBC systems. And some of the benefits that they have shared with us is that they have found several bugs in their mainline interlockings that they were completely unaware of that needed to be fixed. And it has also been a chance for them to rewrite or update their specifications in a more clearer and up-to-date format. And they also say that the approval time, or when things are commissioned, the time it takes to approve it has been decreased, mainly because that since when the software for the interlocking is formally verified and the formal verification checks out, then there will be no problems further down the line. And the next client or next customer that I would like to mention is the Stockholm Metro, or SL as it's called, Storstockholms Lokaltrafik in Swedish. And they are using formal verification for relay-based and computerized interlockings, and they are using the specification-based method, and we have been helping them to derive safety requirements from system specifications, and this is used on basically all the different kinds of rail systems that they have. It's light rail, subway, or metro, and heavy rail. And they also use digital twins for system level modeling, which they can be used for formal verification, simulation-based testing, prototyping, and it supports procurement, tendering, commissioning, and maintenance. And in Stockholm Metro, they don't not only use formal verification, they also use formal methods or similar ideas that we use for formal verification. They also use that to produce application software, mainly basically general applications in the CENELEC sense, with design, test, and safety requirements as formal specification, and we have the actual hardware that this software is running on is we're targeting both Alstom and Hitachi products, but also industry standard PLCs. And formal methods, Stockholm Metro fields give them better control of their system. And it enables competition and a more open signaling system, and it increases quality and drives down life cycle costs. So some concrete examples that we have been working with is Roslagsbanan, which is a kind of heavy rail commuter train in the north of Stockholm, and also Tvärbanan, which is a light rail thing that goes all around the city of Stockholm. And here we have developed application software for the interlocking system, and we have developed a generic application which is used to generate and verify the software used for these installations using our SDA solution. And we also have the green line on the metro or subway, where we have been working with making a formal safety specification, and we've also done verification on an upgrade of the interlockings on a part of one of the lines in the Stockholm Metro, where the computerized system is delivered by Siemens. And finally, we have the red and blue lines on the metro, and Saltsjöbanan and Lidingöbanan, which are light rails. And in these cases, all of these systems are relay systems, and we have done formal verification and modeling of these interlockings and verified that the safety principles are fulfilled. So now over to you, Gunnar.
Thank you. Yes, and to give you a few more examples, we have the Paris Metro, RATP, who has large or long experience of running CBTC systems, but also of formal methods and formal verification. So they have a very competent in-house team doing this technology, and have been for a while, or quite a while, I would say. So they have developed an assessment method that they use in-house that is called PERF. And this is about checking the consistency between models of the systems they get from their suppliers with their specifications. So kind of this specification based verification approach. And over the years, this has been expanded in various ways. So they do also the hazard-based safety verification to make sure that they have not missed anything also in their specification on that level. And they apply it to different types of systems. So it can be for safety critical CBTC functions such as the train localization, computation of movement authorities, and so on. And Prover has been working with them to provide tools and modeling language for this, but also a digital twin or digital model of this environment to be used in the hazard-based verification. And this model is expressed in the SHLL and HLL language, and captures all the behaviors of the system and verification, and the let's say additional systems that you need to model to be able to prove the absence of any hazards. And again, as has been the case in most of these use cases, they do typically discover and has discovered several safety critical bugs that has not been found with traditional verification methods. This might, of course, seem a bit surprising considering the amount of railway systems in the world that has not been formally verified. But one can only imagine that there is a large number of safe critical bugs existing in these systems that are installed over the world, but are not manifesting themselves simply due to that the train operations are typically following a rather standardized method. So they are not just running random trains, they are running trains per timetable with specific operational rules and so on. But of course, there is a bit of a risk there, but there are these kinds of safety critical issues in commissioned systems for sure. So another reason to use formal verification to just sleep a little bit better. And when doing this hazard-based verification, it's of course important to have good tooling to model the environment, but also to analyze the scenarios presented. So here we have worked with them again to use our ProRILOC tool to present this model in a way that it's easy to understand. So that you have, for example, train movements in a visual track layout and so on, rather than having to just dig through text-based scenarios. And moving ahead, we have the last use case to present here. So we have Alstom, as most of you may know, one of the bigger providers of signaling and train controls in the world, among many other things. And they too, like RTP, has strong in-house skills in formal methods and use it globally. Prover is working with them to provide the tooling and modeling language, and of course also training and expert services around this. And they are applying this broadly on different types of systems. So it can be CBTC, ERTMS, and conventional interlockings. And their need, or their why they introduced formal methods and formal verification, was really to answer demand from the end customers. So many infrastructure owners, metros and railways, are asking for it. And as we started off in this presentation, the challenges that we are facing in verification of the more and more complex systems of today. So that also leads to very time-consuming verification processes, and of course also often at a very critical stage late in the project. So you want to cut down on the verification time as much as possible. So to quote them, they say that they have an exhaustive and automatic approach to support the safety demonstration of our systems, talking about the use of formal methods. Yes, and they're also using a combination of the specification based verification, but perhaps even more the hazard-based variant. So actually independently of the implementation, establishing and verifying the safety, so that they can be sure that the formally approved system in the end is safe, and also emphasizing the discovery of issues early on in the design phase. Yes, so some conclusions and a little summary to wrap this up then before getting to the Q&A. So if you would be interested in understanding what formal safety verification can help you achieve, to summarize, it's ensure the safety of your systems. So you can actually mathematically prove system safety with full coverage. It can also help you reduce the costs and delays by using more automated verification methods, and it gives you compliance with the latest CENELEC standards for all safety critical applications. And as we saw in the just previously here, it's been proven in use for a long time at both the infrastructure manager side, so leading metros and national railways, as well as with key signaling suppliers. So it's a mature technology. And to make things easier to get started, we have this packaged solution of the hazard-based verification approach that we call Prover Diagnostic. That can help you eliminate any issues in your signaling system, safety issues, and to prove their absence as well, unlike testing. And if you would like to know more, we'd be happy to schedule a meeting to look at what this could mean for your specific processes and needs and challenges. And also, of course, come up with a plan on how you can implement it and a business case for what the benefit would be for you and the cost as well. So with that, we have a little time left for the Q&A. So over to you, Lars. So I don't hear Lars.
Do you hear me now, Gunnar?
Perfect.
Now we hear you.
Now you can hear me.
Yes.
Okay. Oh, sorry for that. There's something happened with the headset. Well, what I said is that tomorrow, after this webinar, you will receive an email with the contact information, so you can easily get in contact with Prover if you want to discuss this further. There's also going to be a link to the recorded version of this webinar, so that you can distribute it to others or look at it in afterwards. And go back to it if you want to. But now we're going to move into the Q&A and open up and see if there's any questions from the audience. You can type in your questions via the chat functionality that you have in Webinar Geek. So let's see if we have anything that we need to explain or deliver answers for. Well, we don't have anything coming in yet.
We were perfectly clear.
There's one question. At least, let me read it then. I think this is something for you, Gunnar.
Mm-hmm.
Okay, so it is from Christoph, and he writes, many probabilities of hazards are depending on the mood of operations, such as train headway time or junction situations. How does the hazard-based verification take into account this fact? Which hazards are accepted as they are not quite probable? How is this distinction made in this model? Is a timetable simulation needed for this purpose?
Right. So I think this is related to how we model the environment, because the environment can, of course, take timetables in consideration, but normally you would not want to do that because you do not only want a safe system as long as the train are operating per the timetables. But of course, when you do the analysis of the safety hazards, you will have to make some assessment if a potential hazard is unlikely enough so that you can live with it. But that again is not really specific to the formal approach. In any case, when you analyze your system from a safety perspective, you have to make those kinds of judgments. But in general, things like timetables are not supposed to, or the safety is not supposed to rely on a specific timetable. So that is typically not included in the environment model. Yeah, I don't know if that helps answering the question, but it is something that you do have to consider, but it's not that related to the specific verification approach, I wouldn't say.
Thanks, Daniel, for stepping in. I had Webinar Geek who's playing some tricks with me. I can now see that we have another question that I think we have time to answer. How recent is the addition of digital twins to the testing and the verification process, as well as for the hazard analysis methods?
Good question. I think in a way you can say that it has always been used for testing and verification. Perhaps it hasn't been called specifically digital twin, but when it comes to using it more for the analysis methods, when it comes to figuring out what the requirements should be, not only for safety but in general, and to analyze consequences and hazards and so on, then I would say that it's probably a slightly recent development that you do more, at least within the railway domain, that you do more of this modeling, even before you get to the detailed requirement phase of your project, so that already the clients might have digital models of their future systems to ensure that they will meet their needs and requirements.
Okay, thanks for that. We're getting closer to 4 o'clock Central European time and we have to close down the webinar. But I think we actually managed to pick up all the questions, or it was these 2 questions that came in. So with that, I would like to say thanks. And as I said earlier, you're going to receive an email tomorrow with the contact information and also the link to the recorded version. I'd like to say a big thanks for everyone that took your time this afternoon to join us for this 1-hour webinar. So thanks. Maybe some final words before we close down from Gunnar and Daniel.
Yeah, just a big thanks to all of us attended, and please do not hesitate to get back to us with any questions or comments. We'd be happy to discuss.
I can only agree with what Gunnar said. Bye-bye and thanks everybody.
So bye-bye. With that, we close down the webinar, and whatever you do, be careful out there. So see you around. Bye-bye. Thank you.